something you should be familiar with. Yes?
So you said that today we're going to notes, tomorrow we're going to notes, except Friday we're going to play games.
All right, remember that dogma means belief, right? So the central belief or foundational understanding or principle of biology tells us that DNA codes for RNA, and RNA codes for protein. Our foundational understanding of how every single organism on the planet works is that their nucleic acids are used to code for proteins. And proteins are the major biomolecule that makes the body do everything the body does. That's how it works. This seems pretty simple, and it is a slight oversimplification. But overall, if you kind of understand that idea, you're in a pretty good place. The reason that we have to have the dogma of biology is because DNA resides where in every cell? It lives in the nucleus, and DNA is the absolutely good master copy, right? Like it's the one copy a cell gets of all of the genetic material and information, and it is the only copy a cell will get for the duration of its lifetime. When you have things that are exceptionally valuable, you put them someplace safe and you don't take them out. Examples of documents and things that you would be accustomed to doing that with, your birth certificate. Your parents likely have it locked in a firebox in your house. It's in a firebox in your house because it stays there, it doesn't leave, it's proof you were born on the day you were born with your name, and you will need it in the future for various endeavors. There are certain things you can't do without a birth certificate. So say apply for your passport. These are all things that are, going to be important to you one day. Get a Social Security card. That's probably another thing that's a good document that's in your firebox at home. Why? Because without your Social Security number, you're not going to be able to get a job. You use it to apply to college. Those are really big and important things.
What if it was stolen?
Your birth certificate and your Social Security number?
Yes.
If it's stolen, that's usually a very bad thing. That's why they suggest some people keep their Social Security cards on them, which I've never understood. That's a horrible thing. That being stolen is identity theft. People steal your identity, can do whatever it is they choose with your identity. That's bad. Agreed?
What if you tell the police?
They have to they issue you a new Social Security number. Like all of that has to be changed. Very, very big pain. But it ruins your credit permanently. Like even when you contest it and you say, hey, this wasn't me, it's still a ding on your credit score. It's not good. So you keep those things safe. You naturally understand those things must be safe. Same thing with DNA. Has to be safe, can't leave the nucleus. We don't take it out. We're not careless with it. We're not frivolous with it. It stays in the nucleus. But I just said that you need your birth certificate and you need your Social Security number to apply for jobs, to get passports, all of these other things. If it stays in the box, how do I do all that stuff? You do what? You make a copy. You make a cheap, disposable copy. Some of you at home, that means just taking the firebox into the office, putting it on the scanner, making a copy of it, taking your copy in. Yeah, that's what we do. And the copy, you don't just like hand it out on the street corner, right? You're not just like giving it like, hey, you want a copy of my birth certificate? You obviously still take care of it, but if it's ruined or destroyed or shredded or it gets wet, you're not worried about it because it's just a copy. Same thing happens with DNA. We don't ever remove it from the nucleus. We don't ever want to remove it from the nucleus, but it can't do its job if it remains in the nucleus. So we make a cheap copy of it that's disposable, that we don't worry about getting destroyed. That's RNA. That's allowed to leave the nucleus. It goes from the nucleus to the cytoplasm. And you can make as many copies of it as you need. So your birth certificate, it's not like, oh, you can only copy it the once. You can copy it whenever anybody asks for a copy of your birth certificate. So you can make as many as you need, as often as you need. Same thing with RNA. As many copies of RNA needs to be made, they can be made as many times as the cell needs that data. The process of copying it from DNA to RNA is the first process that we learned together. That process is called transcription. And you know I like you to think about the meanings of words, what their parts mean. Trans means across, right? Scribe, God bless you. What's it mean to scribe? To write. So transcription is to write across or to change, right? So you make another copy of it. Back in the day, that's how we used to get copies of really important documents, particularly religious documents. That's how they were copied. We had one good copy. They stayed in a monastery. They stayed someplace safe. And the monks, who were the people who were educated enough to write at the time, their job after they woke up in the morning and they said Vespers, they did all their praying, they did Liturgy of the Hours, they did everything they're supposed to do, then they would go to work. And some of them, their work was to sit down with a section of the Bible or whatever religious document it was and to look at it and then write it. Read it and then write it. They transcribed one copy, the good copy, to another copy. So that's what we do here is transcription. We take one copy and we rewrite it. Granted, it goes from DNA to RNA, but those are nucleic acids. So that's just a slight, tiny change. We then have to go from RNA in the cytoplasm. It's going to be used to make protein. It's really just a recipe for making protein. It tells us the number of amino acids that go in each protein, and it tells us the order of amino acids that go in that protein. So how many amino acids are there?
20.
There are 20.
Wait, so the RNA tells the protein how many?
Well, the RNA tells the builders how many amino acids go into a protein and the order of those amino acids. So we know there's 20 amino acids, and we say, okay, with those 20 amino acids, the RNA is going to say, well, you should use this amino acid 7 times. You should use that amino acid 8 times. And here's the order you should put them in. That's what the RNA says. That's the data that it has. So, protein, we're just going to write amino acid at the top of that so you have it. You know that's what we're talking about. That process takes it from the language of RNA, changes it into the language of amino acids, and because we're changing language, we're going from the language of nucleic acid to the language of amino acid. We call that translation. And you get it. Translation. Translate. Change languages. You translate all the time. Right? Isn't that part of your foreign language classes? Especially those of you who are in Latin, you get like whole sections of text to translate, don't you? So the process of making protein, so protein synthesis, is simply transcription and translation. So we use those terms interchangeably. Protein synthesis is transcription and translation. You okay? Did you hit your funny bone?
Yeah.
That's the worst. I'm pretending he didn't just laugh. I empathize that.
It's funny when other people hit their funny bone, but not when
Oh, so you engage in a little morose delectation when other people hit their funny bone.
Yeah.
That's a sin.
I'm sorry.
Jorge.
Yeah. I'm sorry.
Jorge, I was gonna invite you to
Well, you don't believe in karma.
No, I don't believe in karma.
Left
I
is the
just
best
realized
medicine,
that,
so I mean, right now, he's just curing her funny bone.
I don't get that.
People also name their kids Bronx and North.
Isn't that,
Yeah.
why would you name a kid that? Like, do you want the teacher calling your kid up in front of the class because of trouble? North.
No, I would just get confused when you're learning north, south, east, and west.
So the first step of this protein synthesis process, we said we go from DNA to RNA. So I want to make sure that we make something that to you guys probably resembles a Venn diagram, T-chart, whatever it is you want to call it. A little compare and contrast of DNA and RNA. DNA, you can tell me all about it. Dazzle me with your knowledge of DNA. What's its structure? How many strands does it have? What 4 nitrogen bases does it contain? What's its purpose? What does it do? So it's a code. It's a storage code, right? It's a code that stores information. It's double helix, has a sugar phosphate backbone. Oh, what sugar does it contain in that sugar phosphate backbone? RNA, on the other hand, is not a double helix. It's a single strand. It only has one strand then, since it's single-stranded. And we have a slight change in the nitrogen bases. There is still adenine, there's still cytosine, and there's still guanine. But instead of thymine, we have uracil, U. One little change. Rather than storing information, it transmits information. So it transmits information. And one other small change, instead of having the sugar deoxyribose, it contains the sugar ribose. And all that stuff that you know about the sugar deoxyribose is also true for ribose. So it's a 5-carbon sugar. You can label the carbons 1 through 5. The only difference is that ribose contains 1 extra oxygen. So at a corner of that little pentagon where you would have seen just a hydrogen attached in deoxyribose, in ribose there's an oxygen and a hydrogen attached at that little corner.
So it has a ribose backbone?
It's still a sugar phosphate backbone, but the sugar is ribose instead of deoxyribose. And it makes sense when we think about the name deoxyribose. We've just been repeating sounds we heard, right? But now, D means without, removed, right? Oxy, oxygen, ribose. So it looks like a ribose with 1 oxygen removed. It's the only difference between the two. RNA has the extra oxygen. Yep. So there's one other difference in that DNA really has one form, right? It's that double-stranded helix thing stored in the nucleus. RNA is in the cytoplasm, so locations are different as well. DNA is in the nucleus. RNA can move to the cytoplasm. And DNA is just DNA. RNA, there are 3 kinds. 3 kinds of RNA with 3 different jobs. First, we have messenger RNA, sometimes abbreviated lowercase m, capital RNA. It's the one that moves from the nucleus out to the cytoplasm to transmit the information. It shares the message that's been stored in DNA. Then we have transfer.
Can you repeat the messenger one? What is?
So it takes the message from the nucleus to the cytoplasm. So it's the message, the code that gets transmitted.
What's in parentheses? Sorry.
mRNA, the abbreviation. It's just lowercase m, capital RNA. The other 2 types of RNA are transfer RNA, abbreviated lowercase t, capital RNA, and ribosomal RNA. Lowercase r, capital RNA. Transfer RNA and ribosomal RNA are both in the cytoplasm, and they play very important roles in the translation part of protein synthesis. So they have jobs in translation. So we'll encounter their functions later. But that's where they are, that's what they do. So here's how this thing works. This is clearly double helix, right? So what are we looking at? We're looking at a stretch of DNA. And in that stretch of DNA, there's a little section of it that codes for a particular protein. Any section of DNA that codes for a protein we call a gene. So that's what RNA, that's what we need a copy of. We need a copy of the gene coding region. That's what we call it. The gene coding region. In that gene region, we need the whole gene. So think about this. If I needed a recipe for something and I opened my cookbook for that recipe, but I didn't want to keep the cookbook out, because like there are some cookbooks that, hey, are really expensive. So I'm going to copy the recipe instead of take it down to the kitchen. I've opened it. What happens if I don't copy the whole recipe? I'm not going to be able to make it, right? Say it's one of those recipes that gets cut up on 2 pages. It starts at the bottom of one and finishes at the top of the other. And I only copy the 1 page that it finishes the top of. It's now useless, right? Serves no function. So we have to be very careful in the process of transcription that we get the entire gene copied. So we don't start copying at the gene itself, which here is labeled gene region. We don't start here. We start just ahead of that region. So that way we copy the whole gene itself. That region is called the promoter. It's the promoter region. And an enzyme recognizes the promoter and it attaches there. So it knows that's where to start. There are some repeating sequences of nucleotides that indicate to us that it is in fact the promoter. Usually it is a sequence of thymine and adenine that repeats over and over and over and over again. So it's just thymine, adenine, thymine, adenine, thymine, adenine for like 500 bases. And that's how the enzyme is like, hey, a gene must start here because that's a lot of thymines and adenines all over and over again. So geneticists have named those regions. It's kind of a funny name. It's called the Tata box because it's thymine and adenine, right? That's what we call it. And it's in that promoter. So the first step of transcription is one that we call initiation.
That reminds me of SpongeBob when they're going through the initiation, they're like, initiation. Sorry.
The things that we think of. So in initiation, we are introduced to our first enzyme, and I know you are shocked and stunned to discover that it ends in the letters ACE. You're even more shocked and stunned to discover that it's called RNA polymerase. You're already familiar with the function of DNA polymerase. Its job is to make the DNA polymer. Guess what RNA polymerase does? Yeah, makes the RNA polymer. Excellent. That's all it does. That's its job. So it recognizes the gene region and it attaches just before that gene region. And in order to do anything with the DNA, it's going to have to open it. It opens it, cuts those hydrogen bonds in the DNA. It opens it up just like helicase would have. It's going to just pop it open. And this is still part of initiation. So RNA polymerase is going to bond right at the promoter. And then Once RNA polymerase is bonded, it opens the DNA so it can be used as a template. It only reads one of the two DNA strands. So it's only going to read one of the two strands. And as soon as RNA polymerase moves past, then the DNA can wind up again behind it. So it doesn't just stay permanently open. It only opens for when you need it, and then it closes. Just like your cookbook, you only take it off the shelf and open it for when you need it for that one recipe. When you're done, you close it and put it back on the shelf. Same thing here. RNA polymerase is going to add complementary bases. So on the DNA strand, when it encounters a thymine, it reads DNA has a thymine, it adds adenine. And when it encounters a cytosine, it's going to add a guanine. And when it encounters a guanine, it's going to add a cytosine. But when it encounters an adenine, that's when it, on the newly forming strand, is going to add a uracil.
So in this one, A equals U.
Yeah, so in this one, A is going to pair with U.
And adenine and uracil.
So adenine and uracil, cytosine and guanine.
So when there's a thymine, it's going to put adenine,
Mhm.
put that after adenine equals uracil.
Yep. As soon as RNA polymerase starts to add complementary bases, we start the second phase. Elongation. And all elongation is that mRNA, the pre-mRNA that's being made, the new thing, the complementary strand, is getting longer. It elongates. So it adds complementary bases. So if the DNA reads then the RNA polymerase is going to add A, it'll add a what? T, it's going to add. G, it'll add. G, it'll add. C, it adds. T, it adds. A, it adds. I'm sorry. Woo! Ah. Ah, eraser. T, it adds what? A. And then A, it adds U. So that is the strand that would be made. That's the complementary strand in elongation. Yep.
So it doesn't add complementary bases in initiation, just elongation?
It adds like a small primer, and then as soon as like the second base is added, then it's elongation, and initiation ends.
What's the word after complementary?
Bases. I should tell you, RNA polymerase is as equally limited as DNA polymerase was. Remember, DNA polymerase could only read the template from 3 to 5? RNA polymerase can only read the DNA strand from 3 to 5. That's how it knows which one it's supposed to use as the template strand. It attaches to the DNA strand after the promoter region. It attaches to the 3' side and reads that strand. So
So it does the same thing with like Okazaki.
it won't have to because it's not going to read the other strand. Since it only reads one strand, it reads what you guys would consider the leading strand. And that's the only one it has to deal with. After elongation, you're like, really? That's all it does? Yeah, it just adds complementary bases. After elongation, the last step is called termination. RNA polymerase continues down the template from 3' to 5' until it reaches the end of the recipe, right? As soon as it reaches the end of the gene coding region, it has to stop. But that end, much like we had the ta-ta box at the beginning that said, hey, start here, the end we have a sequence we call the terminator region. So it just says, done, end. And when it reaches the end, RNA polymerase falls off, and we're done transcribing.
So the end of the gene is the term.
So our product so far looks like this. Oops. It's a single strand, and each one of these represents a nitrogen base. So we have on the bottom here, our strand is our sugar phosphate backbone made of ribose and phosphates. And each of the lines that is perpendicular to it is a nitrogen base. So now we have to edit this product. The product is called pre-mRNA. Then we edit it. In that editing process, the first thing that happens, we add a cap of adenines. Actually, check that. My cap is not adenine. My tail is adenine. I do believe the cap is an inverted guanine. So it's backwards. So we put this like hat on it on one side, a cap. It's made of an inverted guanine, so it doesn't get read or used in the making of the protein, because you don't want to use it, because it's just a protective piece at the top. And then we add a tail called the poly-A tail. And it's poly-A tail because it's like adenine, 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 added to the end of this molecule. So then I'd put my cap on and my tail on. But we're still not done editing. You add the cap and the tail, and then you splice. Splice just means to cut. So if I were to splice something, I would cut it. Every gene region has sections in it that do not code for protein. Geneticists call these regions introns. They are non-coding bits of RNA that occur in this sequence. So here, my codons, I'm going to make them, or my exon introns, I'm going to make them blue. So here's like a stretch of 3 of my nitrogen bases that don't code for an amino acid. So they've got to get cut out because they don't do anything. And then next to that is a region of, let's say, 4 that do code for protein. We keep those. Those are good. And then after it, we have 2 more that don't code for protein. So there's an enzyme that just comes through here and cuts out the blue regions that don't code for protein, and then moves the tail over and moves the cap over, so all I'm left with is the coding DNA, or the coding RNA. The ones that don't code for anything, we give those a specific name. The ones that are non-coding, we call introns. And the ones that do code, we call exons. And what's actually really interesting is that in a eukaryote, we don't always splice the same way. There are multiple ways to edit this thing depending on what we're trying to make. So we call it alternative splicing. We could splice it this way where we cut out both introns and are left with just that exon. Oh,